Pre-calculus. Today we're starting Unit 2 in pre-cal material, and it's actually Section 3.1 in your textbook. It's on symmetry and coordinate graphs. The first major topic is point symmetry. Point symmetry is a figure that is symmetrical with respect to a given point. That point can be the origin if it's on graph paper, but it doesn't necessarily have to be. It can be rotated 180 degrees about that specific point and appear the same. So if a figure has point symmetry, you can basically rotate it 180 degrees, so upside down, about a specific point of rotation, and if it appears the same, exactly the same picture, then you can say yes to point symmetry. Take a look at my first picture here. The point of rotation is point A, which I have marked on my diagram. And in order to tell if this picture has point symmetry, I need you to imagine that this point is going to stay constant or in the same place, but you're basically taking this picture, moving it, and I'm moving it clockwise. You can go either direction, but I'm going to go from left to right. And if I moved it 90 degrees, it looks like this. If I move it 180 degrees, then that's the diagram. And so we can see, obviously my A is upside down now, but my picture remains the same. My point's in the same location, that did not move, but my picture has been rotated 180 degrees and it still looks identical. And so this one would be yes. Yes, it has point symmetry. And you can abbreviate like I'm doing. Okay, picture 2. The point of rotation this time is on the origin, so I want you to imagine that this is graphed on graph paper. If I rotate it 90 degrees, which is a fourth of a turn, looks like this. 180, which is a half of a turn, looks like this. Again, the point of rotation hasn't moved. The picture isn't looking exactly like the original. It's moving in the same direction, and it's obviously in the same quadrants as well. Again, this is the original picture, and this is 180 rotation. I want you to also notice that if I did happen to go counterclockwise, again, it doesn't matter what direction. It's still going to look identical for this particular picture. So, question 2 is also a yes. It does have point symmetry. Example 3. I have drawn a parabola. My center of rotation, I did forget to mark, so let me put it here. I want it to be at the origin. And I want you to notice, again, as I rotate a fourth 90 degrees, and then 180 degrees. And so not only has my point moved, but my picture is upside down as well. And so for that reason, this one, the third diagram, does not have point symmetry. So that would be a no. No point symmetry. Again, I want you to make sure that you understand me carefully, because when I say point, a lot of times I have students think that that is always going to be the origin, and it does not mean that. So you're going to have to look at the types of problems you're given, look at the point of rotation, look at the direction they want you to move it. If the directions does not say what direction to rotate, always go actually counterclockwise. You should learn that in geometry, so go backwards, but always go 180 degrees. If a graph has point symmetry, this is the algebraic way to prove it. F of negative x is equal to negative f of x. F of negative x is equal to negative f of x. So what does that mean? That means if I put a negative x into my function and the result is the opposite of the original, when I substitute negative x value into the function, if it causes the f of x or the problem or the y values to be negative, then it definitely clearly has point symmetry. The first option is using a graph to prove that. Okay, so if I'm substituting negative x value into the function and I'm looking to see if the y values change, then this is how that's going to work. Example, if I give you a function f and it's the cubic function x to the third, I'm going to use my table x and show the work inside here and then use my last column to fill in my y values. I'm going to start with negative 2, negative 1, 0, and 1. Stick with the basics. So for the first one, it's going to say f of negative 2 is equal to negative 2 quantity cubed. Okay, well that's going to be negative 8. So you can't stop there though. You got to make sure that it does happen for all of them. So you're going to go with negative 2, you get a negative 8. When I put a negative value in, I got a y value back that is negative. You're going to see that's going to happen on the next one as well. When I substitute a negative x value into the function, I get back a negative 1. And so basically my y value is negative. Then we'll evaluate f of 0. And we'll try f of 1. Okay, so it looks like just from those 4 values that I selected that the function is or does have point symmetry. You also can take a look at it with respect to like the graph. So at negative 2, negative 8, I'm going to estimate that to be here. Negative 1, negative 1, 0, 0, 1, 1. And if I had used 2 earlier, 2 cubed is 8. Kind of giving you an idea of what this looks like. And you saw sketches of these in Algebra 2 last year as well. So there's my cubic graph. And so what that's asking you to consider, again, whether you think about it, this is the algebraic approach, or you think about it in terms of what I did on the first slide, like moving the graph, rotating it 180 degrees. If you focus on my picture right now, and the point of rotation is the origin, the question's asking if I take this entire picture and rotate it 180 degrees, is this piece going to land down here, and is this piece going to land up here? And the answer to that question is yes. So y equals x to the third does have point symmetry. It has origin symmetry, actually. Sometimes the textbook will use that language instead of point. They'll say origin. This is the algebraic approach, and this is the graphic approach, and you do need to know both. Okay, determine whether each graph is symmetric with respect to the origin. Just said that word. When you think origin, that obviously is a point. So this is, like I said a second ago, the textbook sometimes uses that language. So when you see those directions, it's basically asking you to just figure it out, see if it's like point symmetry. We'll start with f of x equals x to the sixth. And we're going to do the same thing we did on the last problem. We're going to substitute some negatives, 0, and positives in there just to see if it's actually going to be consistent and work. So that's my suggestion that you choose different types of numbers, some negatives and positives. Okay, And so you're going to substitute a negative 2 in for the x, and that's going to be a negative 2 quantity raised to the 6th power. Now, if it's a negative 2 raised to the 6th power, remember to use parentheses in your calculator. That way you're the calculator's interpreting your problem. Negative multiplied 6 times together is going to give you a positive answer. If you don't use the parentheses, some calculators will give you a false answer, so please be careful there. And you're going to go through and evaluate all of those very quickly and figure out what you get for your y's. If you put negative 1 in place of x, so I do want you to show this work in the middle of your table, you're going to get back a positive 1. If you do a 0, you're going to get back 0. 1 to the 6th is still 1. And positive 2 to the 6th, 2 times 2 times 2, 6 times is 64. Okay, you also can go to your graphing calculator if you want to, and you can just type this into y equals to see what the graph looks like. F of x equals x to the 6th is actually and this is going to be a rough sketch because these numbers are real big. So let's say negative 264. Let's play up here. Negative 1, 1, 0, 0, 1, 1, and here. So it is symmetric for sure. But this is what the graph's going to look like. On the calculator, it'd look a little bit better. Like different curves there. We'll learn a lot more about y to the 6th later in pre-calc. But this is a similar picture. It's not a parabola. There's some things going on down here that's hard to see, and sometimes it's hard to see on the calculator too, unless you use some decimals and fractions. But the question is, what's the point? Does it have point symmetry? And so if I take this picture and I rotate it 180 degrees, it's going to go like this. And so that's obviously not going to land on top of itself. It's going to look different. And so f of x equals x to the 6th does not have point symmetry. Okay, and tying it back to the algebra, when I put a negative x into this function, I did not get back a negative y. Look at your table. You got back a positive. Okay, so right there was a clear indicator, a big hint as to why this answer is no. You'll have different types of examples, scenarios, asking you to do different practice problems both ways. I would grab my calculator though for sure on the graphing part on this one, because we have not in pre-cal yet, we've not learned the shortcut method to graphing this type of problem. So like I said, just grab your calculator, have it handy there. Oh, let's see what's going on if we substitute these values in. And I'm going to write one out and then give you time to just work through it. You know the process, so when you're on your own, you know you have to show all these steps. Be careful on I chose negative 3, so when I put negative 3 in for x on top, it clearly is negative 3. But the bottom says 1 minus x, so I'm going to do like 1 minus a negative 3. Be really careful there. Make sure that you don't miss that sign. So the top's going to stay negative 3, obviously, and the bottom is going to now become 1 plus 3, which is 4. And so negative 3 fourths, negative 3 comma negative 3 fourths is going to be 1 point on this graph. And you'll work through and do negative 2 next. Negative 2 divided by 1 minus negative 2. the top's going to remain negative 2, and the bottom is going to be 3. Then you're going to have to do negative 1. Negative 1 divided by 2, that one should be a negative 1/2. Okay, we'll move down to 0. 0 on top, 1 minus 0 on the bottom is just 1. 0 divided by 1 is still 0. Then we'll evaluate 1. 1 divided by 1 minus 1. Let's see how that one looks. 1 divided by 1 minus 1. Well, that's the same thing as 1 divided by 0. And that is a problem. And so there will be times where, especially in this type of graph, type of equation, where you substitute a certain number in. Let me fix this. Alright, so a second ago 0 gave me 0. But 1, we saw it didn't work, so when it doesn't work, just leave a little blank in your y value, or in your table. Like that. Okay? I just kind of ran out of room there. Alright, so you'll get all your values, you'll go back and you'll look at it from a graphing perspective. But let's look at it algebraically next. If I put negative x into this function, notice my y value is negative. That's a good sign. When I used negative 2, I also got back a negative. When I used negative 1, I did the problem, but I erased it a second ago. Let's see. Negative 1 divided by 1 plus 1, that's negative 1/2. So I know that's negative. When I put a 2 in there, 2 divided by 1 minus 2, let's see how that works. We also have to check out these positive numbers. Okay, so watch closely here. This one's going to give me 2 on top and a negative 1 on the bottom. Well, that obviously is just negative 2. So when I put a positive in for x, I get a negative back for y. Okay. Alright, so you'll do all of that, then you'll go back to your graphing calculator, you'll go to the y equal button, and you'll type in x divided by 1 minus x. You'll look at the graph on your screen, and then if you're deciding about point symmetry, I've told my students in the past, and several people have liked this idea, just type it in your calculator, look at the graph, and draw me a little sketch on your paper what you saw. But then when you're trying to decide if it's point symmetry, take your calculator in your hand and literally turn it upside down. And if your calculator screen is still showing the exact same picture and it basically landed on top of itself, then it does, yes, have point symmetry. Okay, that's a really good way to do that. So you can turn your calculator upside down, look at the screen, and then make the call. Okay, next is on line symmetry. Line symmetry, you have done, I know, multiple times, even probably back in grade school, kindergarten, first grade, like the easy stuff. But we're going to look at it from not just a graphing perspective, but also algebra. Graphs that have line symmetry can be folded along the line of symmetry so that the two halves match exactly. Some graphs have more than one line of symmetry. So when you're taking a look at like the parabola here, when I say some graphs have more than one line of symmetry, I'm referring to there's different ways to draw lines. You can draw lines horizontally, you can draw them vertically, diagonally, and so forth. So what I like to do is just take a look at the picture. I'm going to start with vertical. If I were to draw a vertical line in that position, if the left side of this graph can be folded over, so you're flipping, okay, you're not rotating, but you're reflecting or flipping, and it lands exactly on top of this, then it does have a vertical line symmetry. And then you also will have to check out, like, put it on top of the x-axis and see if it works. Well, if I imagine this blue piece being flipped over that line, flipped over or reflected, that's going to do this. It's going to model more like that. And so it's not going to be folded on top of itself. So x-axis symmetry is what I call it. That one did not work. The y-axis symmetry did. And then you also can look at it from a perspective of like y equals x, that's a diagonal line, and also y equals negative x. So there's 4 different ways I want you to look at every single picture and decide what kind of lines of symmetry they have. You're going to call it x-axis symmetry if and only if your graph can be flipped over from top to bottom and it land on top of itself. Y-axis symmetry, you're going to have to check to see, like if I drew a dashed line on top of the y-axis, will this side match this side? Y equals x, let me write this one down. Y equals x is the graph of a diagonal line with a slope of 1 and an intercept of 0. We just call it y equals x symmetry. And the one that's falling downhill, this line equation is represented by y equals negative x because the slope is negative 1 and it goes to the origin. So again, those are the 4 I need you to check. Okay, my picture for number 2 was supposed to turn out to be a nice circle, and it does not look like it on the screen, and I apologize for that. So I need you to kind of picture a really good circle in your head. And we're going to start with x-axis symmetry. So let me try that again. X-axis symmetry. Can the top of the circle be folded onto, like flipped over, and it land on this? And the answer for that would be yes. So let me write this down so you know how I want you to do it. So x-axis symmetry, which is a line symmetry, of course, you would say yes. That's called horizontal or x-axis symmetry. Then you would test out the y-axis. Can you draw a line, dashed line on top of the y-axis and this side flip over and look like this side? And the answer, if it's a circle, is yes. Third, does it have y equals x line symmetry? Can I draw a line with a slope of 1 and a y-intercept of 0, and can this part of the circle be reflected and flipped over to land on top of this? So would this fold on top of this, is the question. You got to be good visualizers here. Fourth, y equals negative x. Okay, does that have line symmetry across y equals x? Negative x. Well, that means draw a diagonal line with a negative 1 slope through the origin. Now I need you to picture, does this piece of the circle, can it flip and land on top of the green? Hopefully that helps you visualize. So can the yellow flip over and land on the green? And the answer to that question is also yes. So there are some pictures that actually work for all 4 lines of symmetry. And then I'm going to add one more question in there, just because we've already done this for the first part of the slide. Does this picture have point symmetry? So you'll look back at your definition, and point symmetry deals with rotations. So can I rotate this picture around 180 degrees and it look like itself? And the answer to that is yes. Now let me backtrack, because for some reason I forgot to write down the answer over here. For the first one, on the parabola, it did not have x-axis symmetry. So we would say no. On the y-axis, it was able to flip from left to right, and it did look like itself, so that would be a yes. On the y equals x symmetry, which is this line right here, this piece and this piece is not going to match this when it folds, so this is a no. And then last, on this one, y equals negative x. So we're focused on this line right now. This piece doesn't fold and match this. And so the answer is no. So remember, with these two, you got to look diagonally. Alright, and so the same deal here, and I'll do this quickly. Start with x-axis symmetry. This top half would fold onto the bottom, so this would be a yes. Okay, and then we're going to go with y. Will this graph flip or flips or reflect from left to right? So if I drew a line of symmetry down the y-axis, would this side look like this side? And the answer to that is no. And then you'll go with the other two as well. Okay, so let's call that y equals x symmetry, or line I should say. And again, you're having to picture it. Does this flip over and land here? It does not. That's a big no. And last one, y equals negative x symmetry. And then you're focused on the blue. Can this piece flip over this direction? Nope, it's going to go here instead of here. That's the answer to that is no. Alright, so I did the best I could on a video trying to show you like how you're supposed to picture these. And that's what I need you to do with your own. And so very briefly, the four that I mentioned were the x-axis, the y-axis, y equals x, and y equals negative x. Those are common lines of symmetry. In order for a picture to have x-axis line symmetry, it is obviously going to have to be symmetric across the x-axis. In other words, the point in the first quadrant up here is going to reflect and land in the fourth quadrant. That's what that picture is illustrating. If it has y-axis symmetry, just like I modeled in the last slide, making sure you're with me, it means that a point in the first quadrant, let me highlight that in green, would be able to reflect and land in the second quadrant in the same position. If it has y equals x symmetry, it's going to be that diagonal line again with a slope of 1. A good way to tell if it has y equals x symmetry is to take like a point in the first quadrant and see if it lands still in the first quadrant, but like if this point is 2, 3, then this will be 3, 2. So like the ordered pair will change. The x and the y coordinate of the ordered pair will change. And it's likewise it's going to happen down here. Like in this picture, if I have a point in the third quadrant and I'm trying to see if it reflects over, if the point, let's call it that, if this point and this point are related and the same distance from that dash line, then that's symmetrical as well. And then the last one's y equals negative x. And a good way to think of this is if you can take maybe just one point and flip it, like one at a time would help you see it. That's also a good way to do it. And if they all land the same distance away from that line, you're good. Okay? Alright, so I'm going to get rid of this language. This is what I think the textbook used. But I'm going to use x's and y's instead. Because now I've got to show you how to do this algebraically, because some of your practice problems in the textbook are going to ask you to prove if it has line symmetry algebraically, and so they don't want you just drawing a picture and doing what I did. They want you actually using this. So if it's x-axis and you're trying to prove if a graph has it, you're going to substitute xy